Okay. So once you determine what the molecular shape is going to be, the next thing you need to be able to do is determine whether the molecule as a whole will be polar or not. So when you look at a... one second, let me get my pencil. Okay. If we take a look at CO2, for example, in the molecule, you've got an electronegativity on carbon of 2.5. On oxygen, you've got 3.5. So there is going to be a dipole in this direction, as indicated by the little arrow here, and as well as in the opposite direction. Now, because of the geometry, these two dipoles are of equal magnitude but opposite in direction. So if you think kind of like in physics how we have vectors, these two would effectively cancel each other out. So when your dipole moments cancel, that means the molecule as a whole is nonpolar. So as we draw these diagrams, you need to visualize the angles of these dipole moments and whether or not they would be additive, like summative, or whether they'd be canceling. And then if there's any result left over, that's what we call a net dipole moment. So if we look at a different example, in this case here, you've got a dipole moment bonding towards the oxygen from the hydrogen, and the same thing in this direction. Now these two do not cancel, right? If we break this down, these dipole moments have horizontal and vertical components to them. And what is canceling might be these horizontal components. Those would be canceling, but the result is this. When you take these two and sum them, you have a net dipole moment. And that is going to be the justification for determining whether a molecule is polar or not. All right? Simply stating that, oh, this molecule has a lone pair, it's polar, that is not an explanation. That's an observation, right? But the explanation has to be rooted in the understanding whether the dipole moments cancel or not. So ultimately, that is the answer that you should provide whenever you're asked to explain why a molecule is polar or not. Okay? So just looking at some examples here, if we have a simple molecule like HCl, there's a net dipole moment here because you only have two atoms. There's really no geometries to consider. There's no, you're not adding dipole moments together. You're just looking at it. It's a simple molecule. That's polar. Carbon tetrachloride, you've got four dipole moments, but they are all equally geometrically opposed. So they actually do cancel, and that's why this molecule is nonpolar. In the trigonal pyramid, you've got three dipole moments without the fourth to cancel that direction. So that's going to be polar. This molecule, CH3Cl, this is a chlorocarbon, or chloromethane. You have a dipole moment because even though it's tetrahedral, the dipole, one of the atoms is a different element, right? So you've got your dipole moment up here and then facing upward, and there's nothing of equal magnitude that can cancel it, so therefore it's going to be skewed, it's going to be polar. And then BF3, equal in all directions, completely canceling. Okay, so when you're determining whether a molecule is polar or not, you need to evaluate each bond. Is the bond polar? If so, which direction is the net dipole moment facing? It always points toward the higher electronegativity. And then second, do they all cancel? Okay, it's not simply about that there's just a lone pair. Stating that there's a lone pair is not enough of an explanation. Okay? All right. So, valence bond theory is a theory that is used to explain how we see some of the molecular shapes that we see. So a lot of this theory you already know, we just didn't call it valence bond theory. So a pair of electrons can be shared between two atoms when their orbitals overlap. Now, this is not something we talked about yet, orbital overlap, so this aspect here is new. All right, so for example, hydrogen and fluorine. So hydrogen's electron is in the 1s orbital. Fluorine has 7 valence electrons. The bond that it's going to make with hydrogen, that particular electron will be in a p orbital. So when these two overlap, that covalent bond, that space where that covalent bond exists, is a result of overlap of two half-filled orbitals. The strength of this bond is going to be proportional to the amount of overlap. Atoms tend to form bonds as strong as possible, and this is recalling back to that energy diagram that we talked about the other day when we talked about distance and energy. How there's an optimum distance. That distance is where you get the maximum attraction with the minimum repulsion. That establishes the bond length. So the hydrogen and fluorine atoms will lower their energy as they get closer and closer to each other. Eventually they'll settle into a position where it is most stable, and that's what we establish as the bond length. And it's presumably here where we have the greatest amount of orbital overlap. And then if you push them too close to each other, then they start to repel more, and then the energy starts to rise, and it's not stable. Okay, so let's walk through the different geometries we see and the reason for those geometries. So something with two electron pairs. If we look at an element like Be, beryllium's valence electrons are in the 2s subshell. Now, one of the assumptions is that in order for bonds to form, each element should have a half-filled orbital for every bond that is to form. Okay, so in looking at beryllium right now, it does not have any half-filled orbitals. So presumably you look at this and you think, oh, well, that can't form any bonds. But that is not true. There's a process of the electron promotion called hybridization. And so what happens is beryllium, being in a second period, does have access to a p sublevel. And so what's going to happen is one of those s electrons is going to be promoted, and by being promoted just meaning kind of nudged or moved. And the result is this. We now combined, we have averaged the S and P sublevels, and these are now what we call sp3 hybrid orbitals. There were only two electrons to work with, so one of them moved. The reason why it's called sp3 is because the first was from the S sublevel, whereas the back three were from the P sublevel. So when you combine them, they're just called sp3 hybrid orbitals. Now, in doing this, in hybridizing those sublevels, we now have half-filled orbitals, and we now are capable of forming bonds. So, energy-wise, we need to understand that if the s orbital is at this energy, and the p orbitals are at this energy, then the hybrid orbitals, because they have been averaged, are going to be somewhere in between. So somewhere in between, but closer to the p's, because there's more p orbitals than there are s orbitals that factor into the averaging. So it's weighted towards the p's. So that's why it's higher up than down. When we draw Be Cl2, for example, we draw the Lewis diagram to look like this. And these bonds here, this bond here correlates with this orbital. This bond here correlates with this one. Okay, so this is a simple 2-electron pair molecule. Let's work our way up. Oh, this is what they look like prior to hybridization. This is what your S looks like. This is what your P looks like. When we average the two together, then we have 2 orbitals, which in sum result in this shape here, which correlates to the linear geometry and the 180-degree angles that we expect. Now, this diagram shows the fluorine and its orbitals and what they're doing, right? But the point is, it ends up in a linear shape, and we did know that it was going to be a linear shape, but this explains how it rearranged its valence electrons to make that happen. Okay, let's try 3 pairs. So, BF3. All right, we expect 24 electrons. We have mentioned before about how boron is an exception in that it doesn't hold an octet. It's too small. The electron pairs would be too closely crowded, so that's generally why it's not seen. But in looking at its orbitals, boron is 2s1, 2p1 prior to bonding. The hybridization process will result in that s electron being promoted, and we will now have 3 half-filled orbitals. And, oh, you know what? Sorry. I need to jump back. Let's jump back to this guy here. I need to amend this. This is not sp3. This is my bad. This is just sp. We're only recognizing the orbitals where the electrons actually made it into, so we actually have 2 half-filled orbitals. So this is what we call sp hybrid orbitals, because one was from s and one was from p. The 3 that were vacant, we don't count them. So the first hybridization type is called sp. That is when there are 2 electron groups on a central atom. Back to the one we were just on here, this is going to be called sp2, because 1 was from s and 2 were from p. And the fact that boron now has 3 half-filled orbitals means boron can form 3 bonds, which is what we see here when our molecule forms. Okay, are you guys with me so far? Is this making any sense? When you look at an orbital diagram by itself for a lone element, sometimes it is not apparent how many bonds it can make or how it's going to bond. So it shuffles its valence electrons around so that it can form half-filled orbitals so that bonds can be made and orbitals can be overlapped. Okay, 4 pairs. So something simple like methane, CH4. So methane is going to form what we call the tetrahedral geometry. But when we look at its orbitals, it's S2P2. But we clearly see that it has formed 4 bonds. So something must have happened. So that s electron is going to move to the fourth, or to the last p orbital, and then we have a hybridization with sp3. 1 from s, 3 from p. That's where the name comes from. And now that it has 4 half-filled orbitals, it's going to form 4 bonds and result in the tetrahedral shape that we expect right here from this guy. Individually, the hybrid orbitals look like this, and because they're all over a common origin, the resulting shape is the tetrahedron. Okay, now let's talk about expanded octets, because we did say that you're going to see atoms that have the ability to hold more than 8 electrons, and they can do so if they have access to a d subshell. So let's say we had a molecule like this, PF5. 5 plus 35 is equal to 40. So the Lewis diagram would look like this. You know, octets all around. So we got 5 bonds. So how did this happen? Let's look at phosphorus's valence electrons. Gesundheit. It's S2, P3. Now, unhybridized, just regular on its own, phosphorus has the ability to form 3 bonds right off the bat. It's got 3 half-filled orbitals. It does have the lone pair, right? So, but in this case, where we're forcing the issue and it's bonding 5 times, in order for this to bond 5 times, you're going to need 5 half-filled orbitals. So because phosphorus does have the d subshell, we're going to promote this electron here into that first of the d sublevel. And so the result is what we call sp3d, because there was 1 from S, 3 from P, and 1 from D. Oops. Five half-filled orbitals, 5 bonds. Okay, and so the last, something like SF6. Sulfur has 6 valence electrons natively, but clearly we see it's in a molecule with 6 bonds. So it's going to use its d subshell. It's going to promote 2 electrons. And give us an sp3d2 hybrid. I didn't mean to make that guy far apart. I'm going to bring him closer. There we go. Okay, so for hybridization, the purpose of hybridization is to rearrange valence electrons so that we can have half-filled orbitals that can overlap. Half-filled orbitals are a very easy configuration for covalent bonds to form in. There are 5 hybridizations. They align to specific number of electron groups. They just increase predictably. So what we need to do is we need to be able to, after drawing a Lewis diagram, ascertain the hybridization of the central element, or any element really. Any atom in a molecule we can determine the hybridization for based on the number of electron groups that it has. Okay, so example. XEF4, the one here in the bottom right. So 8 plus 28, we're looking at 36. Xenon in the center. You got fluorines, 4 of them. Each is complete. Now at this point, I have used 32 electrons. I need to use 36. So put a pair here, put a pair here. A pair of electrons, a lone pair of electrons counts as an electron group. So therefore, a xenon falls into which hybridization class? So xenon, but how many total pairs? Yeah, the biggest one. 6 electron groups, 4 bonded, 2 not bonded. If you have a double bond or a triple bond, those count as 1 electron group, right? So here, let's change this guy here. Let's change this to CO2. When we draw CO2, it looks like this. The central atom, carbon, has how many electron groups on it? I didn't ask for the number of bonds. I said how many groups, how many areas where there are electrons? Just 2. And hybridization of that is then sp. Now, another way you can, if it helps to think of it this way, is that your hybridizations do correlate with angles, bond angles. Bless you. So the sp, of course, is 180. The sp2 is the 120. The sp3 is the 109.5. sp3d has 2 angles because the trigonal bipyramid has 2 angles. Depending on your perspective, it's either the 90 or the 120 if you're looking at it from top down or from the side. And then sp3d2, everything is 90. Okay. I probably went more into the detail of the process happening. At the end of the day, what you need to be able to do is you need to be able to draw the Lewis diagram and determine its hybridization. Okay? So I don't mean to make it sound bigger than it is. All right, but that's the reasoning, and this here is what you need to know. Okay? All right. So lastly, before our lab, let's talk about sigma pi bonds. Whenever a covalent bond forms, electron density is concentrated along the internuclear axis. What that means is it's concentrated between the atoms. Right? So very simply, if I had a bond like between 2 carbon atoms, and I said, where are the electrons in this bond? Well, of course, the electrons are going to be between the 2 atoms. That's the internuclear axis. This bond in that location is what we call a sigma bond. And a sigma bond has the Greek lowercase letter. It looks like this. Kind of like a cursive O with a tail at the top. Okay, so sigma bonds, this is your typical covalent bond. All covalent bonds form with electrons concentrated between the atoms. However, we have seen multiple bonds, things like double bonds, things like triple bonds. When there are double and triple bonds, the additional electrons that make up that double or triple bond cannot be in the same place as the original bond because there's be too much repulsions. So, as a result, the electrons in the double bond occur above and below. I'm going to add some space here just so I can better illustrate this. Okay, so for example, let's say we have something like this. Okay, this is ethene, C2H4. There is a double bond. Now, if we break this apart and look at this, kind of like we were using ball and stick model, so obviously those are the C's, these are the H's. Okay. Let's look at carbon's hybridization process. Carbon, before bonding, has orbitals that are arranged this way. We look at carbon and we see that carbon has 4 bonds in total. 2 bonds to hydrogens and 2 bonds to the carbon. So that's 4 bonds total. So if it's going to make 4 bonds, there had to have been some hybridization that took place. So we'll move this guy into here. And so we now have 4 half-filled orbitals. Okay. Pause there for a second. Let's go back to this diagram here and label these guys. So I'm just going to call this A, B, C, D, A, B, C. Okay, well, problem is that in the simplistic diagram that I drew on the right-hand side, I did not show you the D bond yet. And that's because the bond in a double bond has to occur above and below the plane. And that is possible because it's using a p orbital, but specifically an unhybridized p orbital. Remember how p orbitals look like dumbbells? Well, they look like dumbbells unless they're averaged or hybridized, but this last orbital was unhybridized. That's why it still looks like a dumbbell. So that carbon is doing that, and the carbon on the right is identical, so it's also doing this. And so what that does is that provides an avenue for electron circulation above and below the original bond. So the electrons here, they are able to circulate back and forth above and below the original bond. And this is what we call pi bonds. Each pi bond has 2 lobes, like 2 lobes, like that, right? From 2 unhybridized p orbitals. So these green arrows here circulating above and below, this area here and here is the second bond. It's the double bond. The first bond, A, B, and C, are sigma bonds because sigma bonds are direct overlap. This bond here is the pi bond. Okay, so what I'm trying to say is that every time there is a multiple bond, the first bond formed has to be a sigma. Anything additional is a pi bond. Because in order for a secondary bond to exist, it cannot conflict with the original bond that formed. It would not be stable. So it's the second bond, the form exists above and below the plane of the first bond. Okay, yeah, Nick.
Is this because they repel each other so much?
Yeah, because there's going to be 2 repulsions if they're all concentrated in the same place, right? All right, we're going to stop this here.